Hello, welcome to the second video on ODEs, ordinary differential equations. In this video, I'm going to talk about some general properties of ODEs, including how many solutions there are. So in general, ODEs, if you simply have a differential equation, will have infinitely many solutions. And in order to specify a unique solution, we need to add some other condition, which is usually an initial condition. And so we're going to discuss in general how this works in this video and look at one particular example. In the next videos, we'll look more specifically at techniques of how to find the solutions. All right, so let's start out by just considering really the simplest possible ODE. The simplest ODEs are ones where we simply have the derivative of a function. So dy dt equals some function of t. Y only occurs in one place. This is a first order ODE, in fact, a first order linear ODE. And note we could have a different independent variable, x. In the second one, x is the independent variable. In the first one, t is the independent variable. But in either of these cases where we just have that dy dt or dy dx is some function, we can solve just by integrating. And so actually this is what you do when you integrate. You find all the possible functions whose derivative is equal to a given function. And that's really solving an ODE if you think about it. Really a very simple ODE. And so if you're able to do the integral explicitly, you get this solution, and there's an arbitrary constant in it. And this is called the general solution. This arbitrary constant corresponds to the fact that there are infinitely many solutions of the ODE. There's infinitely many functions y whose derivative is a given function f. Right? And in this simple case, we just would find y by taking the indefinite integral. Right? And this is called the general solution. It's still the general solution even if you can't explicitly do this integral of a function f. Right? There still exists this general solution. There is a function whose derivative is given function f. Right. A key point here is that there is not a unique solution. The general solution contains this arbitrary constant, c, and c can have any value, which corresponds to the fact that there's infinitely many solutions of the differential equation. There's one arbitrary constant. Okay, now let's start talking about more general first-order ODEs. And what we're going to discuss are explicit first-order ODEs, which are ODEs that can be written in this form. The word explicit here refers to the fact that we can explicitly solve for the derivative of y, the dependent variable. So we can write the equation in this form where there's the derivative on one side and the derivative equals some function of both the independent variable t and the dependent variable y. All right, so y appears in two places here in this equation, so it's not a simple matter of integrating in order to solve the equation because we wouldn't know how to integrate the right-hand side. Okay, so in general, there's no simple procedure to solve all explicit first-order ODEs. We're going to look at a few procedures that work in some cases, but there's generally no way to find all possibilities. This is sort of similar to the fact that when we're doing indefinite integrals, you can't find an indefinite integral of an arbitrary function. For example, e to the negative x squared. We thought about that one when we were talking about numerical integration. There's no formula for the indefinite integral of e to the negative x squared in terms of the elementary functions. Right? And there's generally no way to solve this differential equation because it involves both y prime and y. So we have some examples of these explicit first-order ODEs. Some of them are linear, some of them are nonlinear, but they're all first-order. So this first one here, see, this is a linear equation. The left-hand side depends linearly on y and the derivative of y. And we could write it in this explicit form if we subtracted y to the other side of the equation. The second one here is nonlinear, but again, can be put in this form by subtracting cosine of y or adding cosine of y to the other side of the equation. This one is also linear, but it can be put in you can solve for dy dx. And this one is nonlinear, you can solve for dy dx. So again, an explicit ODE. All right, let's consider an example of an explicit first-order ODE. So here's one. It's put in this explicit form where we solve for the derivative. And, well, one solution of this ODE is y equals 1 plus t. And I haven't told you how to define that, but I'm just telling you that is a solution, and you can easily check, because it's very easy to take the derivative of this function. 1 plus t, the derivative is just 1, and that equals y minus t. That's 1 plus t minus t. Right? So this is a solution of the differential equation. However, there's other solutions as well. So for example, another solution is 1 plus t, the same solution as before, plus e to the t. Right? And you can see this if you differentiate 1 plus t plus e to the t, you get 1 plus e to the t. That's equal to the right-hand side. In fact, there's an entire family of solutions with an arbitrary constant. And this is very similar to what happens when we have the simple ODEs and we solve just by doing an indefinite integral. You have an arbitrary constant, c, which appears in the solutions. In fact, you can multiply this exponential e to the t by any constant c, and that is still a solution of the ordinary differential equation. And you can check that yourself by plugging this formula in, c is a constant, and checking that it satisfies the ODE for any value of c. Right? This is called the general solution. In fact, all solutions of this differential equation are in this form. So it can be written in this form, 1 plus t plus a constant times e to the t for some constant. And when we say general solution, we need an equation for solutions that includes all the possible solutions. Now, generally speaking, for first order equations, a general solution is going to have one arbitrary constant. And this corresponds with it being first order. Right? Second order equations, generally speaking, there's two arbitrary constants, and the number of arbitrary constants corresponds with the order of the equation. You can think of this very roughly as just being that in order to solve a first order equation, you have to do something like integrating once, and that introduces one arbitrary constant. For a second order equation, integrate twice, two arbitrary constants, and so on. Right? So for first order equations, this is just what I was saying. First order equations, the general solution will usually have one arbitrary constant. And in fact, for linear equations, it's always the case. So for linear equations, there's always just one arbitrary constant. Nonlinear equations, it can be more complicated, but for many cases, there's still one arbitrary constant. All right. So if we just have an ODE, you get a solution, a general solution, which is a formula that includes all possible solutions, and there's an arbitrary constant. This arbitrary constant will be fixed by an initial condition. So, for example, you suppose that y equals 0 at t equals 0, y of 0 equals 0. Then you could solve for the arbitrary constant using this condition that y at 0 equals 0. And if we plug in t equals 0 and y equals 0 to the general solution, we get that c equals -1, and that gives us a particular solution of the ODE. The particular solution that satisfies the differential equation and also the initial condition. And in this case, it would be c equal -1. That c is the constant in front of the exponential. And so the particular solution would be 1 plus t minus e to the t. Okay, so this is the solution for the example that we looked at a few slides ago, the ODE with this initial condition. And if you're given the solution, it's easy to check whether or not it is in fact the solution. You take the derivatives, plug it into the equation, check, and also check it satisfies the initial condition. But of course, it's harder to find that solution in the first place if you're not given it. So what we're going to look at over the next few videos is how we can find these solutions. Right, and there's still a little bit more about the general theory of ODEs before we get there, though. An important fact about ODEs is that, in fact, if you have an ODE that can be written in this explicit form, right, so an explicit first-order ODE where we can solve for the first derivative and be nonlinear, and you specify the value of y at a particular t, the particular value of the independent variable, so an initial condition like this, then there is exactly one solution of the problem. Right? So you just have the ODE, infinitely many solutions with an arbitrary constant, but then once you specify the initial condition, you can solve for the arbitrary constant, and that gives you exactly one solution. Right? There is one caveat to this, which is that, in fact, if this function f, if it's not continuous, or if its partial derivative with respect to y is not continuous, then it's possible that this could fail. There may be no solution, or there could be more than one solution in some cases. Right? These are sort of odd cases, can be important in some applications, but we're not going to look at that any further. What we're going to focus on is methods of solving ODEs. It is, however, important to realize that there are solutions, and if you specify an initial condition, then the solution will be unique. All right, so let's look at another example of solving an ODE with an initial condition. And so this would be an application. Suppose we have some number of bacteria in a petri dish. Y will be the number of bacteria. And since the bacteria will be growing very large, so there'll be many, many bacteria, we'll just consider Y to be a real number. Of course, in actuality, Y would be an integer. But we'll model it as a real number and say that the increase in the size of the population of bacteria, so the increase in the number of bacteria, is proportional to the number of bacteria. So dy dt is the derivative of y, that's the rate of increase in the size of the population, is proportional to the size of the population. So is some constant a times the size of the population. A is the rate at which the population is growing. Okay, this A could be positive if the population is growing, possibly negative if the bacteria are dying. All right, and also we know that we need to have an initial condition in order to have a unique solution of the problem. If we don't specify the number of bacteria at a given time, then we can't determine the number of bacteria later either. And so let's say at a given time, t equals 0, there are 10 bacteria. All right, so let's consider the solution of this problem. Switch over to the visualizer for this. So what we have is a function which is growing at a rate that's proportional to the function itself. We're going to look at how to solve this in the later videos, but you may recognize that a function that grows at a rate that's proportional to itself is an exponential function. That's in fact the definition of an exponential function. And so let's guess that y is an exponential function. So guess that y and t equals e to the lambda t. Lambda here is a constant. We'll determine it by putting this into the equation. Then the derivative is lambda e to the lambda t. And if we put that into the differential equation here, then you see you have lambda e to the lambda t equals a e to the lambda t. And this is true for all t if lambda equals a. And so y is a solution of the differential equation if y equals e to the at. And so y of t equals e to the at is a solution of the ODE. All right, and so this is one solution. Of course, we know that there are infinitely many solutions from what I discussed in the previous slide, the existence of uniqueness of solutions for ODEs. What are the other solutions? Well, here you can see that if you multiply both sides of the equation by some constant, then the constant times y would still satisfy the equation. So if we have one solution, any constant times that solution still satisfies the equation. So in fact, the general solution in this case is y of t times c times e to the at. All right, this is the general solution. And let's now find a specific solution that satisfies the initial condition. So the initial condition is that y at time 0 equals 10. All right, so if you plug in time 0 here, you just get that 10 equals c. And so the particular solution that satisfies this initial condition is y of t equals 10 e to the a t. Right, so this would be the function that would give you the number of bacteria in the petri dish. All right. So this is the solution to this problem, but of course it's a bit unsatisfying since I just waved my hand and said this is exponential growth, so we'll guess that y is an exponential. Now, how do we know that that's the solution? Well, there are constructive ways to find this solution, and that's what we're going to cover in the next few videos. So in the next video, we'll talk about a method to do this that's called separation of variables.